Development of multi-winding transformer-assisted diode-based converters for improved utility interface, done by Group 16, supervised by Professor J.P. Karunadasa. Digital electronic field have been developing drastically in last few decades with the invention of transistor. Solid-state devices are utilized in number of applications in present world due to availability, fast data transferability, reduced power consumption and low cost. They are used in various industries like electrochemical, mining, transportation, and aerospace. Those semiconductors-based devices are operated under DC current. Therefore, AC to DC converters are essential in current world, because electrical power transmitted as AC. AC to DC converters are available with different number of pulses like 6, 12, 18, 24 and 36. But using AC to DC converters cause several problems like harmonic injection and AC voltage distortion at utility side, DC rippled output and poor power factor in consumer side. Therefore, designers, manufacturers and users should obey several standards and guidelines when designing, manufacturing and installing AC to DC converters. We designed an AC to DC converter to mitigate the previously mentioned issues. Our objective is to develop a multi-winding transformer-assisted diode converters for improved utility interface. And our scope is to reduce the THD at AC side current down to 5% with minimal or no separate filtering and to produce DC output in desired value with ripple factor 0.1% or better. These are our design specifications for the proposed converter. In order to achieve the objective, scope and specifications, we have designed, simulated and analyzed a 96-pulse AC to DC converter. This diagram illustrates the proposed converter configuration. Input is operating on 400 volts, 50 Hz three-phase system, while output operates at 750 volts DC and 25 amperes rated current. This converter system is mainly consisted of two multi-winding transformers, 8 full-bridge converters, a zero-sequence blocking transformer and an interphase transformer. There are two main multi-winding transformers in this circuit. One is delta double extended delta transformer. These are its circuit configuration and the core arrangement of the delta double extended delta transformer. And other one is star double extended delta transformer. These are its circuit configuration and the core arrangement of the star double extended delta transformer. Basically, multi-winding transformers provide 24 phases AC waveforms. There are 8 diode converters which are used to obtain 48 pulse DC output. This diode converters rectify the AC waveforms, and those waveforms are having different phase shifts. If we take the first rectifier, the first phase is 3.75 degrees leading with the input phase of voltage. And other two waveforms of that rectifier have 120 degrees phase shift with each other. Same goes with other converters. Those 8 diode converters are connected as 2 sets by connecting 4 diode converters in series. So, they provide 48 pulse rectified waveforms. Those 2 rectified voltage waveforms are going through zero-sequence blocking transformer. It is used for connecting parallel diode rectifiers and to ensure the independent operation of 24 pulse rectifiers. After that, load is supplied through the interphase transformer. Interphase transformer is used to fulfill main 2 aspects, which are double the pulses and reduce the harmonics in supply line current. Therefore, in this, pulse doubling process is done and gives resulting 96 pulse DC output. This is our MATLAB simulation for the converter. This is the 3-phase AC supply. This is multi-winding transformer. This is simulated using multi-winding transformer block. Ratings of all the transformers are taken by product of delivered voltage and current of them. These are the diode converters. They are connecting 2 set of series connections. This is a zero-sequence blocking transformer. This is the interphase transformer. Performances can be evaluated using MATLAB simulation. In this project, we are mainly focused on THD levels of input current and voltage, ripple factor of output voltage and the power factor of output. Different blocks are used to evaluate the previously mentioned quantities. Performance can be evaluated for different load conditions by changing the resistance values. After setting appropriate resistance value, we can evaluate the performances by running the simulation. It will take several minutes to run. Then we can obtain the intended performance values. And we can get the required waveforms. This is a performance of the converter for different load conditions. If we consider about the THD of the input voltage, it is increasing with the load. At full load condition, voltage THD is reduced to 0.2%. Current THD is almost decreasing with the load, and it has its maximum value around 0.1461%. Variation of the current THD is 0.089%. Power factor also increasing with load, and it has almost 0.99 since half load condition. In addition to that, this converter has lower ripple factor. This is the input voltage waveform for the converter and it is almost having a sinusoidal shape. This is the input line current waveform for the converter. This also has approximately sinusoidal shape. This is the harmonic spectrum of the input current waveform. There is considerable contribution from 47th and 49th harmonics. This is the output DC voltage of the converter. There are 96 pulses in the periodic time interval. There are 2 transformer units and each unit has 10 kVA rating. And this is a small rating transformer. Therefore, rectangular shaped limb can be used. This is the estimated dimensions for the one transformer core. These are the number of turns required for the primary windings. Number of turns for the secondary windings of both transformer units are same. These are the estimated costs for the copper conductors and the iron core for transformer units. This project proposes a multi-winding transformer-assisted 96-pulse diode converters for improved utility interface, reflecting the input voltage THD, input current THD, displacement factor and ripple factor for varying load conditions. So, with the emphasized power quality aspect values, it can be clearly state that this proposed system is an effective approach for improved utility interface.